So good afternoon. Hope you've had the coffee to stimulate you for the sessions that are to follow. So just to introduce myself, I'm Lisa Jackson. I'm based in the Aeronautical and Automotive Engineering Department, and perhaps coming at this failure theme from a slightly different perspective, or I feel it from a slightly different perspective, and I'm welcome from the conversations we've already had to see what parallels and how we can learn from different instances of failure. So I'm presenting it from a systems level perspective. And I would say that from an engineering point of view, we've actually embraced the concept of failure, not necessarily successfully, but we have actually, the term failure is flagged up, it is used as we go through the design of new products and new systems. Now, most of us use systems every single day, transportation systems, for example. You will have commuted from your place of home to here today, but I bet you never even thought about whether you failed to make that journey. You just got in your car, got on the train. It's not necessarily something that we think about, and part of that reason is there's been a huge raft of knowledge and modelling that's gone on behind the scenes to ensure that the systems that we have are reliable. They will do what they are intended to be designed for, the purpose that they were designed to do. But that does not mean to say that failure will not happen. You know, failure is inevitable, as has been alluded to in the presentations that we've already had. There's just two pictures on the screen here of incidents which has happened in the last couple of months. The first one, the Baltimore Bridge, where the tanker went into this bridge and ultimately resulted in fatalities. And one of the things about failures in engineering is we have the concept of fatality. The second one there is the Alaska Airlines 1282, which had to go back to the airport after starting off this flight because the door fell off. Now, in this particular case, there weren't any consequences in terms of fatalities, but of course there'll be other consequences associated with it. So we have the concept of when we're developing a system, but also if something does happen, then we will analyse how that failure happened to try to learn. I think one of the key things about failures, especially in engineering, is that we hope to learn from those failures to prevent them from happening again. So in the first instance, they're not completed yet, but there's information about that particular tanker that was having power issues earlier on when it was having maintenance, had an electrical blackout. There's some concept at the moment about a crew member that mistakenly removed a damper, which caused the power outage when it was in motion and had no engine control. In terms of the latter bit, in terms of down here, in terms of the aircraft, we've got part of the analysis that's looked at, there's missing bolts in that particular door. And actually there was flags in terms of a lighting mechanism, which indicated there was pressurization issues in that craft, although it was allowed to fly with restrictions. Now, some of you might be alarmed about that. That's actually a natural policy in airlines, that they can have a time and dispatch concept, and we could spend ages talking about it, where you can have failures and you actually can fly for a certain period, depending upon what that failure is. So failures do happen. But we've really moved in engineering from a sort of trial and error through to a formalization. So actually it's very different in engineering, I think, about the appreciation that failure does happen and how we design such that we try to mitigate it. This is not an extensive timeline. We've got 10, 15 minutes and I probably will overrun. But there's some key points in time and actually reflective of world wars and the impact that they have and the things that happened in there, which has made us change how we accommodate failures. So first of all, one example in the First World War with aircraft, we had a trial and error approach. So when those planes were damaged, the engineers had to redesign those aircraft to get them operational again. So they had to change the design slightly to try to learn from the experience of what they've watched or what they can visibly see, to change the design to get it back operational and flying again. So it's a bit of a trial and error approach to improve that design, to make it better. We also had the introduction of the thought about comparing one engine planes versus two engine planes, and will that actually improve its flight potential. In the Second World War, had great impetus from the missile and space industry. So they started actually trying to quantify reliability. They started to bring in failure rates for things. So you had to make sure you didn't have more than 1 in 100,000 flying hours of failure. And also there was metrics for landings that you had 1 in 10 to the 6 before automatic landing and 1 in 10 to the 7 failure rates with automatic landing. So we started off that process of kind of quantifying and having that standpoint of deciding at which point failure could happen, determining what that point was. There's a German mathematician, Lucer, who actually started to look at components and questioned the weakest link concept, actually to look at the components themselves. And if there was variability in those components, that could actually influence failure. So it started to address the issues of quality and thinking about how to assure quality in our products. And then we've got the US military. They became particularly interested in this area because they had many failed pieces of equipment during those wars. And that's really beneficial because you'll see later on, we had other instances in the 1950s with other wars where equipment costs, and what I mean here is about repair costs and maintenance costs, was actually really high. So for every $1 spent on a piece of equipment, it was $2 to actually repair or maintain it. The UK military resources, over half of it was on maintenance. So what we've led to in the engineering domain is actually standards, initially by the military. The MIL standards is commonplace, and now standards exist across all domains. So automotive, we've got ISO functional safety 26262, for example. So we kind of embraced those failures in engineering. This is a really simple word cloud. In my conversation to you in what was 3-4 minutes, I've mentioned some words: failures, risks, consequences, reliability, maintenance. There was a person in there, so we've got human errors. There are lots of words within engineering. So we have our own language about failure. This is something I think Michael's going to follow up with after my thing about the language that we might use. So this is our language, but it might be different across the arts and the sports and the other domains that we are going to talk about. So I tried to encapsulate those kind of words into sort of 4 generic statements, if you like, about failure in engineering. So I broke it down to failure modes, failure analysis, failure detection, and failure mitigation. And I'm just going to give it, because of your broad reach of subjects, I'm hoping some of you this may seem obvious, and others, I've been told with engineers we actually think slightly differently to other people, be that good or bad. So I'm just laying out in this kind of logical process, and I think this is partly how we apply that logical process in failure analysis. So first of all, failure modes, how do things fail? And really we can look at this from a component level and a system level, because within a system we have components. And I'm using components in a generic kind of sense of the word here, because there's lots of types of component failure. So traditionally mechanical systems, so we have mechanical failures. But nowadays systems are more complex. There's electrical parts potentially, there's chemical parts within it, there's thermal failure modes. There's aging modes, there's environmental factors which influence that. There's humans, we still very much have humans in the loop, and they are a law unto themselves that happens within engineering systems. We have software, and again, we had an instance that Mike produced in the first about the software of the post office, for example. As we move to more autonomous systems, the level of software is going to increase, the level of integration is going to increase. And every single way of those components were factored in software and humans under the title of components, they can all fail in multiple different ways. So if they can all fail in multiple different ways, so can a system. So what we need to do is identify what those system critical failure modes are. And this is a difficult one in itself. And this is where we perhaps relate to risk, because it's not criticality. How do we define those critical system failure modes? Of course, the things that happen with the large consequence, we don't want to happen. Those big media stories that we see typically affect lots of fatalities. But we've also got the things that happen a lot. So it might be little consequences, but if they happen all the time, then actually that is something that we need to consider, something that comes into a risk calculation. There's loads of challenges still in this space. You know, we've been analysing components and systems or trying to determine how they do for a number of different years. We've got new systems, we've got new energy systems, new powertrains, for example, in cars. We're going to use batteries. They're out there, but are they going to last as long as we want them to do? We've got fuel cells, for example, got new components. How do they fail? Okay, we've got to do a lot of testing to try to understand them. New system architectures with multiple functionality, the combination of all of these things together. So there's still a lot of unknowns and a lot of uncertainties in this space. The second bit is failure acceptable? So if we've identified the way things can fail, and they can fail in multiple different ways, so for us, we have a starting point, we have a baseline from which we can assess whether failure has happened, which perhaps is something open for discussion, given the conversation earlier about, is there a definition of failure? So for engineering systems, I'd say there is, and it's different for each particular scenario, but we can debate that. So component levels. We will be doing experimentation a bit like Mark said earlier with regards to the thing on your leg. Yeah, dynamometer, there you go. So you'll be testing to understand, in this case, the component was the leg or the muscles in the leg if you wanted to go to that level of granularity. But we'll be testing those components. We may have, for our area, if it's repairable, we may have maintenance logs, we have historical records of events which we can relate to that. And we can use that information to find out distributions, statistical, quantifiable parameters for those particular failures. From a system level, there's loads of different analysis methods out there in development since the 1940s, 50s, and 60s, and some of them are still used in exactly the same way as they were when they first were instigated. And we have that analysis method because what we want to do is we want to have a form of quantification. We want to give it a likelihood of occurrence. Is this event going to happen, and how often is it going to happen? And if we have that, because we have these standards now, we can assess that quantifiable measure against those acceptability criteria, and hence we can determine whether it's acceptable or not. And as I mentioned in the first instance, if we do have a failure, because we can't prevent it in all cases, then we need to look at what the root cause of that failure is, so we can learn from that and redesign our system to improve it for the next occurrence. And again, there's lots of challenges still in here. So even though we have methods, we need to look at the accuracy of our component data. We've got new failure modes, so we don't necessarily have the large amounts of data. What do we do with limited data? What do we do with those unknowns? We've got a huge amount of dependencies, that interaction between all of those different modes in that system. So you've got both internal things and external factors, and how do they come together? And how do we make sure our modelling actually covers those types of things? So the next one is about detection, but it's actually more than detection, it's about system health management. So one of the things that we typically do now, especially with the Industry 4.0 revolution and the use of sensors, is we're trying to monitor our systems more, such that, first of all, can we detect whether we have a failure? If we can detect it, can we diagnose what that failure actually is? Then can we actually look at, well, we know this is the situation now, what is the remaining useful life of it? What is the lifetime left? And then if we have that system health monitoring capability, we can make decisions on how we further operate it, or perhaps how we maintain it. And this area of diagnostics and prognostics is what our research fellow here, so Dr. Yan, Professor Yan, apologies, will be talking about tomorrow. So we'll be going a lot more into these areas, because in each of these cases, sensors, we'll be looking at, are we monitoring temperatures and pressures and flow rates and so on. And when they deviate from a norm, then what particular thing has happened? And there's lots of different methods, model-based, data-based, knowledge-based methods in the diagnostic and prognostic area. And here we can use the tools like machine learning now to enhance our capabilities to uncover and diagnose what that fault is, such that we can try to make our output as successful as it possibly could be. There's a huge realm of things that happen in the space. This is one of the areas I'm working as well. I'm particularly interested in seeing Professor Young's talk tomorrow. But where do we put our sensors? What are those sensors should we use? Within our system, where can we put them so we don't disturb operation? How can we improve our level of diagnostic capability? And how can we then look at that prediction? Can we really use machine learning? Is it with machine learning, you need lots of training data for accurate models, but if you've got new systems, you have no training data. So there's lots and lots of challenges in here. And the last bit is about mitigation. And interesting conversation over lunch, and we were talking different domains with the professor here, and he was talking about deterrence. And I guess this is a similar terminology. We're trying to find out what things we can put in place if we might have a failure, or to prevent that failure. Now, some of it is improving our own inherent reliability of those components or the things that make it up. But other things is about what safety measures or what levels of redundancy or diversity do we have in our system so that we can prolong this time. A big area of interest for mine, for example, is how do we set our maintenance strategy? So if we've got something that is repairable, how do we go about it? When do we do it? And how do we do it? And again, there's lots of challenges in this particular area. So in engineering, it's pretty well defined in terms of going through that product life cycle from the design stage, through the concept stage, through the manufacture stage, through its operational life, and even through the end of life. Reliability and failure measures are in place along the whole of that life cycle. We are quite prescriptive in the way that we do things. So then it made me think, and I'm going to put a sporting one up there. I think we've already highlighted, Marcus talked about, so failure modes, he talked about, we've got biological responses, we've got physiological responses, we've got psychological responses, or mode. I guess it's like each of these can be a mode. There's environmental factors, it could be very hot or very cold. Those are just some of the things that I'm thinking about, and I think we have ways that we can test them. And as Mark has alluded to in your talk, with one very example about your muscle fatigue and stress and strain. Failure analysis. It appears to me that it's very after the event, it's reactive to a failure event. But this could be wrong, this could be a conversation. You know, is there anything that happens prior to the failure to prevent that failure analysis? Do you look at all of the potential failure scenarios, for example, and decide which is the most critical one, and then set your training regime, for example, or whatever? I don't know. That's something that just came into my head. And then you've got
about 5 fields of sports science.
And then, you know, failure detection, and of course we've got sensors, we can monitor our own heart rates and things. I know if we're going fast, you know, too fast or what we expect, but that's an interesting area in terms of how do you get those symptoms, or can you diagnose what's actually happening, both physiological, psychological, whatever, and then be able to mitigate against it with suitable things. Should you slow down in the middle of the marathon? Not so easy in a 10-second or 8.9 is the world record now with 100 meters for men. So I thought it's really interesting that I had some questions that maybe we could answer throughout the week. You know, is the language the same? I think we've got a quite prescriptive language in engineering. It will be good to explore whether that is across other fields. There's some similarities, and I'm sure there's some differences. And can other disciplines learn from our kind of prescriptive message? Maybe they can, but also can we learn from other disciplines too, in terms of the way that we approach failure? So that was me, the whistle stop talk.